We're going to start with 1.1. So the first thing here is a definition of a function. A function is a rule that assigns to each element x in a set D exactly one element called f of x in a set E. So it's a rule. A function is a rule. Basically, it takes in a number, spits out a number, right? The domain of a function is the set of values which may be evaluated at or all allowable points of the function. So we've seen in the past in college algebra and in pre-calculus, there's certain things you can't plug into certain functions, right? Like if you have the square root of x as a function, you can't plug negative numbers in. So the domain is everything you can plug in. Let's see who remembers some pre-cal. What would be something you cannot plug into the function f of x equals secant x? Secant x. So if I take f of x equals secant x, someone give me a value, a number that is not in its domain. Anybody remember what secant x is? 1 over cosine. 1 over cosine. So this is 1 over cosine x. Good. Now, what could potentially cause a problem if I have 1 over cosine x? If I have 0 in that denominator, right? So if this denominator here, cosine x, is 0, I've got problems. So maybe I should look at that. When is cosine x 0? So where's cosine 0? Dun, dun, dun. So are you thinking unit circle here? Straight up, 90 degrees? That's correct. 180 also. Or not 180, you're 270 straight down. Yeah. So if x is 90 degrees, or let's do radians, pi over 2. And another one would be x is 270. Or what's that, 3 pi over 2? And actually, there's infinitely many, aren't there? Those are things that would not be in the domain. All right, let's get back to it. So the domain is basically everything that can be plugged in. The range of a function is, for each value we plug in, something comes out, right? As long as we can plug it in, there's something that comes out. If we take everything that comes out of the function, that's called its range. It's all the outputs. Okay, now the concept of independent variable versus dependent. The variable which takes on the values from the domain, oops, there's going to be typos, okay, sorry. Domain, I spelt it wrong. Usually x is called the independent variable. It's independent of the other variable in the equation. The value is independent of the other variable in the equation. So x is what you plug in, and what's the dependent variable? The one that comes out, right? The y. We usually have an x and a y, or x and f of x. So in order to know what y is, you have to know what x is. So y depends on x, so y is the dependent variable. Graphs of a function. The graph of a function is a visual representation of all the inputs and their corresponding outputs. It is the set of all ordered pairs, and then I've got this thing over here. What the hell does this mean? Well, yeah, this is like a point, like the point 2, 4, right? The x and the y coordinate. It's all the x and y coordinates for every x. That little symbol means element of what? The domain. So for everything that you can plug into the domain, all the outputs, write them out as points, ordered pairs, that's your graph. So the first way we ever learned to graph something was by doing a t-table. Remember this method? You would have like y equals f of x equals negative x cubed minus x squared. So let's do this by graphing 5 points. Let's just pick some points. So what's the independent variable here? What's independent? X. And the dependent one is y. So if I plug in an x, and I just picked -2, right? I could have picked anything I wanted, but I picked -2. All I have to do is plug -2 in here, blah, 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 and it would spit out 4, right? Then I could plug in -1, it would spit out 0. If I plug in 0, I get 0. If I plug in 1, I get -2. If I plug in 2, I get -12, right? If I plot those 5 points, this is what I get, right? Get that graph right there. Those are my 5 points. Everyone's comfortable with that, right? Now, 5 points is sometimes 5 points is enough for you to know what it looks like. But a lot of times 5 points isn't enough. So this is that thing I was showing you earlier. I'm going to bring this thing up. There are the 5 points, right? If I had done 25 points, now I get a better idea of what it looks like. If I do 50, there's even more, 100. But who would want to plug in 100 points, right? And then the actual function itself, I'm going to take all those points out. You can see it's that red. And I'm kind of disappointed. This projector in this room sucks. There's some good projectors on campus that you can really make out the colors. This one's not one of them. So, all right. Okay, next idea. This is the concept that f of x, right? That's the output, is the height of the function at a given value. The height being the height if you measure it from the x-axis. I'm going to blow this one up pretty good here. So on this one, you can click and you can drag your value of x. So here's x, right? X is actually like negative, boy, you can't see it there, can you? Negative 2.6. And the height of the function there is this blue line. That's the output, 3.4. So the output is how high you are off the ground. So is the output here positive or negative? Positive, right? Because I'm above the x-axis. And if I move over just a little bit to the right, I'm still positive, right? At some point, though, my height is actually what? Like right in there. I can't get right on it, but you can you can open this up and you can actually put in a value if you want. So there, at 0, what's my height? 0. If I keep moving to the right now, my height is actually a negative number now, right? Because I'm below the x-axis. All right, so we just want to make sure that we understand that the output is the height of the function. Vertical line test. What do we use the vertical line test for? To determine if it's a function, right? So to test if a graph represents a function, that is to say that y is a function of x, we apply the vertical line test. If any vertical line intersects the graph more than one point, then it's not a function. So is this one a function? This is a function because if I pull any vertical line that I draw, right, it will hit it no more than one time. Now if I click on graph B, now I have another function. Now look at my vertical line over here. It's not hitting anything. Is that okay? If you draw a vertical line, you do not hit the graph. Does that mean automatically you're not a function? No, this basically doesn't tell you anything. Right now, I can't tell you. It could be a function still. How about when I move this thing right on top of that? I can't get it. Right on top. Is that a function? How many times do I hit it here? Once. That's okay, right? But as soon as I go to the right of 0, I'm done. And my line turned red to let you know, oops, not happening anymore. So I hit it at 2 places. This fails to be a function. Everyone, I think, has probably seen that. Piecewise functions. Any function that is defined to be different functions on different ranges of the domain is called a piecewise function. So here's an example of a piecewise function. So what this says f of x equals x squared plus 1 if x is less than or equal to 1, and negative x squared plus 2 if x is greater than 1. So what you have to understand about piecewise functions is that there's usually a separation where you have one function that turns into another function. And our separation here happens at what x value? At what x value? At x is 1, right? If I come out here to x equals 1 right here, that's where my function, to the left of 1, it's this guy. And if it's to the right of 1, it's this. Now, why is there a solid dot here and an open circle here? Okay, so and these two pieces right here where we define our domain, it says if x is smaller than or equal to 1, you want to plug in here. So if I plug 1 in, I get 1 squared plus 1, which is what, 2? So I put a dot here, a height of 2. But I do not put anything here. What if I had a solid dot here and here? It would fail the vertical line test, wouldn't it? And it would no longer be a function. How many of you have seen piecewise functions before? Okay. Every once in a while I have to check to make sure my audio is on. All right. Intervals where a function is positive and negative. So now we get into some stuff it's going to be important in this class that you understand how to write down intervals. So a function is said to be positive on an interval I if the function is bigger than 0 there. That just means that if the height of your function is above the x-axis, we say the function's positive. If the height of the function is less than 0, it's said to be negative. That means below the x-axis. And if it's actually 0, then it's said to be 0 there. So let's look at this function here, and let's see if we can't determine where it's positive and negative. So where is this function positive? So I'm saying, where's the height of the function? Where is it above the x-axis, right? That's right in here, isn't it? So from this x value to this x value. Can you tell what x value that is? I think this is -5, right? So -1, -2, right? So it looks like from -2 to where? 0. Now, when you talk about intervals, you're talking about the x values. Where is it positive? Between the x value of -2 to 0. Now, where else is it positive? Well, from 0 to 2, it's negative because it's below the x-axis, right? But from 2 on, it's above the x-axis, right? So here's where I can click on this. And again, the color's not going to come out very good here, but right here, this green, and then this green right here. And then what I did is I put the interval in red over here. And man, that's really hard to see. I'm going to blow this up just so you can see it. That interval right there, that's the way you write it. X is an element of parenthesis, -2 to 0, close parenthesis. What's this symbol? Union, parenthesis, 2 to infinity, parenthesis. Why am I using parentheses and not brackets? They're intervals, but what's happening at -2? What is my function's value at -2? Y'all see my arrow? What is it? 0. Is 0 positive? No. So I don't want to include -2, so that's why I put a parenthesis, not a bracket. And then what's the value of the function at 0? 0. 0 is not positive, so I don't want to include 0, so I put a parenthesis. Same thing with at 2, right? At 2, my function looks like it's 0, so I don't want to include that. And then what about infinity? You always put parentheses on infinity, always, always, all right? Now, where's the function negative? See if you can jot that down yourself. Like, give me the interval answer. What I mean by interval answers, x is an element of what? Uh-oh. All right, well, let's see if you got it. It's negative down here, right? That means to the left of -2. It's also negative between 0 and 2. So this is the correct answer over here. And I'll blow that up a little more too. That should be your answer. Yes?
You have a parentheses where you don't want to include it. However, on the 2 and up, why is that not a bracket?
On the 2 and up?
Like on positives, you use the parentheses because it doesn't include the number itself. But like on infinity, why would it not be a bracket on that?
For the same reason that at 2, at the value 2, right? It looks like I have an x-intercept, which means that my function's value is 0 there. And 0 is not a positive number. So if you try and include 2, you're telling me that at 2, when I plug 2 into the function, I should get a positive number.
What about the infinity?
What?
Because at infinity, it would be included, wouldn't it?
Great question. Infinity isn't a number. That's the idea. That's the reason. If you put a bracket on infinity, you're actually saying that you include infinity. But infinity is an idea. It's an idea of going forever. So we always put parentheses on it regardless. Yep. You'll never have a bracket on infinity or negative infinity, both ways. Good question. I almost mentioned that, but I just was going to let it go. I'm glad you brought it up. All right. Oh, there's one more there. Where is the function equal to 0? Where is it equal to 0? At -2, 0, and 2. How do you write that? What's the correct way to write that? Do you do brackets? You're trying to include it, but it's only one point, right? So here's where we have to understand some notation. Brackets and parentheses are for intervals. That's when you're trying to say between this number and this number. But if you only want to include what we call a singleton, a single value, you use braces. So let me show you. Here's where it's equal to 0 at those 3 points. And I'm going to have to blow this up so we can see it. So what I put is x is an element of the brace. The first brace means a set of points, not an interval, a set of points. And the set is -2, 0, 2. Close the brace. Now it would not be wrong to do this though, also, just so you know. You could have put x is an element, or sorry, you could say something like x equals the single value -2. And you could write x equals the single value 0. Those are my braces. Sorry, they're terrible. 2, like that. You could write them individually. But then you don't say element of, you say equal to. It's equal to that single value. Element is if it's coming out of a set or an interval. Is everyone still awake? Everyone all right? Okay, so that's the idea of positive, negative, and 0, right? So what does it mean for a function then, not to be positive and negative and 0, but increasing and decreasing? Well, increasing means, and this is the actual strict definition of what it means to be increasing. A function is said to be increasing on an interval I if f of x sub 1 is less than f of x sub 2 when x sub 1 is less than x sub 2 on the interval I. What? Okay. And it's decreasing when f of x sub 1 is bigger than f of x sub 2 when x sub 1 is less than x sub 2 on I. All right. What does that mean? It's Kind of. I mean, there's a relationship between those points. What does this first one say? Increasing means that this point is what? The height of that point is below the height of the next point, right? And the first point is on which side of the second point? If I say x1 is less than x2, I'm saying x1 is to the left of x2, right? So that means that the point to the left is below the point to the right, correct? That's what it means to increase. Decreasing means the point to the left is above the point to the right. And you're going to see this in a picture in a second. And constant means what? They're the same. The heights are the same. So let's take a look at the picture. Oh, I went too far. Okay, so I gave us 2 points here. Here's x1, and here's x2. All right? x1 is to the left of x2. Now, what's the relationship between the heights? Which one is bigger? Ooh, this is tricky. Which of these is bigger? The left one or the right one? The right one is bigger. Because you have to remember what a number line looks like, right? Remember with the number line that when we say here's 0, right? Here's -1, here's -2. Which of those numbers is bigger? -1 or -2? Which one's bigger? The larger number's to the right. Now, if you take the absolute value of the number, then okay. So it's a little tricky on this graph to realize that even though this is a smaller height, this number, -2.1 or whatever that is bigger than -6.3. So would we be increasing or decreasing here? If the point to the right is bigger than the left, it's increasing. Now I also put a little thing here. You can click arrow that connects it with an arrow. Hey, doesn't that arrow point up? That's what we mean by increasing. All right. So if we ride this thing like a roller coaster, and just like we read a book, we always read left to right, correct? We always read left to right. So if I sit here and I read this thing left to right, I'm going up, right? I'm going up, I'm going up. The roller coaster flattens out here, right? Just for a second, flattens out. But then the roller coaster goes up and up. And the arrow is actually getting longer, which kind of represents the idea that it's getting steeper, right? All right. That's increasing. Now, what does decreasing look like? Roller coaster, riding it from left to right, but now we're going down, right? The point to the right is smaller than the one to the left. If you put an arrow between those two, you're going down. What about at 0? We haven't addressed this. What's happening at 0? This is very critical. Think very carefully about this. What's happening at 0? It looks like it flattens out, like it's constant, doesn't it? But when you talk about increasing and decreasing, you have to be looking at an interval. So let's say you're picking one of your points. I'm going to come up here on the board. If I pick, let's say, 0 to be one of my points, then I have to pick another point either to the left or to the right. If I pick one to the right, I'm going to be down a little, aren't I? And I'll still be decreasing. If I would have picked the other point to the left, I would have been up. So I still would have been decreasing, wouldn't I? So when you talk about increasing and decreasing, you cannot talk about increasing and decreasing at a single point. Can't. Has to be, you always have to be testing 2 points next to each other. So at 0, you can't say what's happening at 0. You just can't. You can't say, is it increasing or decreasing at 0? What you can say, though, is that this is increasing, or sorry, this one right here is decreasing everywhere. Would you all agree with that? No matter what, no matter where you are on this graph, you're always going to be going down. And then a constant function is kind of less interesting. It just stays the same the whole time, right? So your arrow is flat this time. Doesn't go up, doesn't go down. With me? All right. Determining where a function is increasing, decreasing, and constant. So let's go back to this. I'm going to put this example up here. See if we can get this numerically. Now let's make sure we can see these marks. This is, if I try and blow this up, let's see. Oh yeah, that's a little better. Okay. Where is this function increasing? Where is it increasing? So if you're riding this roller coaster from left to right, where is it going up? And just like we did with positive and negative, you're talking to me, you're telling me your answer in terms of the x values. So from where? -2. You're saying the x value, -2, to where? From here to here, you're going up? Do you all agree with that? I agree that, yes, that's true, but there's more. Like over here, aren't you still going up also? Right? So everywhere over here, you're going up. All the way until you get to what x value? -1. So from -1 to the left forever, your function was increasing. Where else? From 1 down here, right? So at x is 1 to forever to the right, it should be going up. Yes? Good question. It's not incorrect to put a bracket, but I always tell my students, put a parenthesis. So I'm going to show the increasing now. So I click on increasing, and it brings it up. The dotted part is where the function's increasing. So everything over here, then everything over here, and then the red, what does the red represent here on my x-axis? That's my answer, right? Now, it looked like -1, didn't it? It looked like -1? It actually wasn't, sorry. We'll just say it was -1, but it was -2 over √3. That's where this value is. And then this is 2 over √3 is here to infinity. Do you see how my answer is represented? Parentheses on everything. For increasing, decreasing, just always use parentheses. So where's the function decreasing then? Where's it going down? Yeah, I mean, we can still say -1. All right, that's fine. From here, though, right, down until I get to here. So if we stick with the 1 in -1, we could say from what, -1 to 1? Or if we use what those values are, it would be from -2 over √3 to +2 over √3. And that would be also parentheses on both. So there, that would be my answer. And lastly, where is it constant? It's never constant. So how do you say it's never constant? How do you say never? What's that? DNE says does not exist. That's a little different. Does not exist is we reserve that for when we talk about limits of things, which we're getting to, just not yet. The empty set. The empty set. A 0 with a line through it at a little angle is the empty set. It's the set of nothing. Now, again, this is just a little side note for everyone here. Let's look at this. What's the difference between this and this? The top one is a number. It's the number 0. Okay? The bottom one is the set of nothing. So let's say I had a red basket sitting here, right? And inside of it, I put that, right? How many things are in that set, in that basket? One thing is in that basket. What's in that basket? The number 0, okay? If I say here, this basket right here, how much is in that basket? Nothing, okay? So 0 with the line through it is a set. It's the set of nothing, as opposed to the number 0, which is the number 0. Completely different concepts. It's dogs and oranges. They're not even the same type of thing. A set versus a number. Now, I know in the military, I think the military, they do teach to do is a line through the zeros, so you don't mistake it with an O, right?
Well, we phonetically speak out zero. We don't say O as a number, you say zero.
But if you write it, don't they usually say to strike your zero or strike your O or something like that? Okay.
It's preferential.
I've heard it, people tell me from military, like, oh, that's what we use for zero or something like that. That's right. It's all about context here. So in this class, don't ever give me an empty set for zero as your answer. If your answer is zero, you put zero. But don't put zero in a line through it because that means the set of nothing. All right. So it's never constant. Let's try and determine the domain of a function algebraically. Oof. Determine the domain of these functions algebraically. So you have those written down, right? I mean, it's not written down. You have them in front of you. Did they come out on? Yeah. Okay, so I'm going to go to a new sheet of paper and write this down. So let me take this first function. F of x equals x squared minus 4 over x squared plus 7x minus 8. And my handwriting will get better. I've had 3 weeks off, and you know how that is, right? So what am I trying to do? Determine the domain algebraically. Trying to figure out what I can and cannot plug into this function, right? So what are the things I'm concerned about? The denominator can't be 0, right? So how am I going to figure out when this is 0? Probably try and factor it, right? Well, while we're factoring, we may as well factor the numerator also. Just to make sure that we're okay at factoring. What's the denominator factor to be? X minus 1 plus 8, is that what I heard? Okay. So now what I can do is I can take each of those factors, x minus 1. I can ask myself, when would that be 0? And x plus 8, when would that be 0? And that would be at 1 and what, negative 8? Okay, those are the two values of x that I cannot plug in. If I plug them in, I'm done, right? Because the function's going to not be able to handle it. So how do I say everything except those? How would I say that mathematically? There's several ways. There's set notation, interval notation. So you're saying all real numbers except equal with a line through? Is that what you're saying? I haven't seen that one. Okay. I'm not sure that would be as precise the notation we'd want. I know what you're trying to say. All real numbers except the set 1, negative 8. That would be proper. Because this says all real numbers take out these 2 points. Okay? Not equal. I understand what you're saying, but that's not the way we would do it, write it mathematically. Okay, that's one way to write it. You could say x just not equal to 1 or negative 8. You could say the set of x such that x is not 1, x is not negative 8, x is a real number. I mean, there's so many different ways to write this. This says all x such that, that's what that bar means. All x such that x cannot be 1, x cannot be negative 8, but x is a real number. But this is the way I prefer, okay? I like this. Number line. This isn't going to be my final answer, but here's number line, right? When we were doing positive, negative, increasing, decreasing, weren't we doing intervals? I think knowing how to write intervals is a more powerful thing. It's better for later on, so you may as well use them now. How could I say everything except just don't have that, don't have that? You can have everything there, you can have everything there, and everything there. X must be an element of negative infinity to negative 8. Don't include negative 8, right? Union, negative 8 to 1. Don't include negative 8 or negative 1. Union, what? 1 to infinity. Do you see what happens here when I write it that way? It's basically everything. It's longer, definitely. But again, I think it's better for you as a student to get comfortable with intervals. All this does is jumps over the 2 points, right? It's like negative infinity all the way you get to negative 8, jump over negative 8, negative 8 to 1, jump over 1, 1 to infinity. Okay, that's the first one. Next problem was g of x. How long have we been going here? An hour and 15? Believe it or not, we've got to go like another 30 minutes before our first break. And we come back and basically do it again. Does that seem right? That doesn't seem right, does it? We're supposed to go for what, 3.5 hours? Is that what it is? So what's that, an hour 45 twice? Yeah. You signed up for it. I took Cal 1 in the summer. There's pros and cons to it. You don't have a lot of time to forget, but you also don't have a lot of time to swallow or breathe. All right, what about this one? What are the things we're concerned about here? Yeah, there's a couple of things, right? First of all, what's inside of this, right? What's in there, which we call the what? The thing under the square root is called the, anyone remember? Starts with an R. Radicand. Radicand. The radical is the symbol itself. The radicand. The radicand cannot be negative, right? The radicand can also not be what? 0, because what would happen if the radicand is 0? Square root of 0 would be 0, and then you get division by 0. Do y'all agree with that? So we have two issues here. So I'm going to write that down. What we have is this. 4x minus x squared has to be bigger than 0. Strictly bigger, doesn't it? Can't be 0, because I'll have division by 0. And it can't be negative, or else I have a negative under a root. Now, this is what's called a quadratic inequality. A quadratic inequality. And it's very different than a quadratic equation. Because if it's a quadratic equation, we could just try and factor it, set each factor to 0, we'd be done. Or you can always use quadratic formula for a quadratic equation. Quadratic inequalities are much trickier than quadratic equations. So here's my recommendation to you for a quadratic inequality. Either go Google it and look at some YouTube videos on how to do quadratic inequalities, because it's not part of this class, or just follow the method I'm going to show you here. First thing I'm going to do is I'm going to ask myself, when is it 0? So I'm going to turn it into an equation, but just for a moment. And I'm going to remember that I need to come back and look at this as an inequality. Where's that thing 0? Well, what can I do to solve this? Factor out an x, good. I'm left with 4 minus x, right? Set each factor to 0. I'm using something called the zero factor property. You've done it before, but maybe you don't remember what it was called. The zero factor property allows me to set those equal to 0. And now what are my two solutions? 0 and 4. X is 0, X is 4. Now, do I want those as my answers? What would happen if I plug in 0 or 4 according to this? I would get 0 to come out. And I don't want 0, do I, right? I wanted it to be bigger than 0. But why is this useful to me? Let's see. Because if I go to a number line now, and I say 0 here and 4 here, I don't want those as part of my answer, right? But geometrically, okay, geometrically, if I were to take this thing that I'm highlighting now in blue, see if that blue comes out okay. That thing right there, forget the greater than 0. If I told you, hey, that's a function, what kind of function is it? Like when you graphed it, what would it be? Is it a line? What is it? It's curved. What kind? It's a special category of function. It's a parabola, right? Why? Because it's x squared. Which way does that parabola open? Down. Why down? Because I have a negative in front of the x squared. So this is a parabola that opens down, doesn't it? Further, I know that it hits the x-axis where? 0 and 4. So if I came in here right now, let me do this in green. I could actually tell you that my parabola looks like this, doesn't it? And what is it that I want to know about this parabola? When is it what? Bigger than 0? That means when is the function positive, right? Can you tell from this little picture I drew? Between where and where? Between 0 and 4. You see that? Without doing, I mean, I had to know what a parabola looks like, and it opened down. But I'm kind of like using my knowledge of parabolas to answer this domain question. So what would my final answer be? Everything between 0 and 4, but not including 0 and 4. So x must be an element of parentheses 0, comma 4. Done. What if I didn't know what that looked like? Well, that would be a whole different animal, okay? But quadratic inequalities, you can always do this way. If you kind of know what it looks like, you can do it like this. Once you get past quadratic inequalities, you get to like cubic or fourth degree or something like that, then you have to have a little better method, and that's where I would suggest you go look it up. I don't think we're going to run into it, but you've got this great resource called the internet, which I don't think I had that. Well, it was around when I was a student. It just wasn't what it is now. All right, last one. Hey, secant, check it out. Didn't we do that one a little while ago? That was totally unintentional. H of x equals secant x, which we already said was 1 over cosine x. And we had already said earlier in class that we basically said cosine x can't be 0. And we had said that, okay, that could be what? X is 90 degrees or 270. That's where that happens? Yes? Okay, this is extremely important, but it's tricky. So this is where your pre-cal, which all of you passed to be here at some point, right? This is where I'm going to see how many of you know the unit circle well enough. That's a terrible unit circle, but that is a unit circle. How many of you can read trig values off the unit circle? Raise your hand. Like if I ask you what's sine of 30 degrees, if you had the unit circle in front of you, you could tell me. Raise your hands. That's it? Okay. Then I suggest that you put that as a note for yourself to get help with or come to me before class. It would only take about 10 minutes to show you how to read trig functions off a unit circle. But it's vital that you can do that in this class. And you want to get to a point where you don't even need it in front of you, where you kind of just see the unit circle in your head and you can do it. So we said earlier that the two places on the unit circle where you get cosine to be 0 is up here and down here. And that's because what are those points? This first one's 0, 1, and this other one is 0, -1, right? And cosine is always the x-coordinate. So what angle is this? We said the angle was 90, and then the other angle was 270. But that's only two of the answers. There's actually infinitely many answers. So how could I say all of those answers? Because I could keep rotating around, right? Keep on going around. Well, there's some things I can plug in. There's just those I can't. Let me help guide you. Do you agree with this? X cannot be pi over 2. Do you agree with that? Because if it's pi over 2, we're pointed straight up, and cosine of that is 0. Now, if I go and I spin around halfway, that's still no good, right? And if I spin around another half, it's still no good. And if I spin around another half, it's still no good. So if I add something over here, watch this, my pi over 2. What if I say plus, what do we say? A half rotation would screw things up, right? What's a half rotation? Pi. That's 180 degrees. So if I add pi, that would be bad, wouldn't it? How many times could I do a half rotation, though? As many as I want, right? So you can either use a k here or an n is the standard notation. I'm going to put it down here. Where k is an element of z. Anybody know what z is? Everyone knows what script r is. That's the real numbers. But what's script z? Integer. So this is basically the set ... -3, -2, -1, 0, 1, 2, 3, ... forever. All integers. I'm going to go up to the board again because I think this is critical that you understand this. You first have to know, before you can do this, answer this question, you have to know where cosine is 0, right? Cosine is 0 here and here. That's where it's 0. Then you have to realize that, look, if I start here, pi over 2, and I add to it, let's try k is 0, okay? So if k is 0, what do I get? Pi over 2, right? Now let k be 1. Sorry, 1. What would I get? Pi over 2 plus a pi. Pi is a half rotation. So I would go there, wouldn't I? So I get that answer. Then start back here, pi over 2. Now let k be 2. So I'm adding 2 half rotations. 1, 2. Back up there, right? And then I could add 3, and that would have brought me back here. And I keep on getting all these infinite answers, right? Do y'all see this or not? Then what about negative? Pi over 2. Instead of rotating this way, I rotate the other way. And every single one of these answers is a different answer, isn't it? I mean, pi over 2 is pi over 2. Pi over 2 plus pi, what's pi over 2 plus pi? Well, pi is 2 pi over 2, isn't it? I did that to do what? Why did I do that? To get a common denominator? So I put them together and become what? 3 pi over 2? So by adding pi, it becomes 3 pi over 2, which is different than pi over 2. And if I add 2 pi, then I get common denominator again, and I get 5 pi over 2. So you get all these different answers. But this is the general solution. And we did not want our x to be that, right? We said don't let x be those numbers. So that's why I put it like not equals through there. Right? I put that not equal sign through there. No, you in this class you don't have to tell me k is an integer. It would be more proper to do so, but I understand that it would be understood that k is an integer. And like I said, some textbooks use an n there instead of a k. And it's the same thing. N is an integer. So use n or k. All right, that's, oh, we still have a few more. Yeah, we can knock these out and we'll take our, I think we're going to be taking a break. Yep, we are, just after this next example. All right, so anyone who just walked in, you need the notes or anything? Yes, one copy of the notes. How about syllabus? Yes. Syllabus, just you got everything? No, notes, yeah. All right, so I'm on 1.1.19. Determining a function. Express the area of a circle as a function of its diameter. Express the area of a circle as function of its diameter. What does that mean? Wrong class? Oh, man. Would have been fun. All right. What does this mean? Area as a function of its diameter. If I write down f of x, that means I have a function. This function is a function of which variable? X, right? I want, not f of x, I'm going to write it this way. I want a of what? A of d, and I can use capital D or lowercase d, but d is the diameter, right? That's what I want. I want a function that gives me the area of a circle if somebody gives me its diameter. That's what I want. So what is the area of a circle? You have to know that before you begin this problem. If I have a circle, and if I know its radius, area is what? This should be a common formula that you would know. Pi r squared, right? Isn't this equation giving you a relationship between the area and the radius? You give me the radius, I give you area. That's not what I want, though. I give you diameter, you give me area. So what could you do here to this formula to make it in terms of diameter instead of radius? Yeah, you need to know the relationship between the radius and diameter, right? So I'm going to put here, but your radius is always half the diameter, isn't it? Or if you want the diameter divided by 2. Those mean the same thing, right? Half d is the same as d over 2. I would encourage you to get used to writing things more like the one I highlighted in yellow, as you'll see later on in this class. If you have a constant underneath a variable like this, just write it as a fraction out in front. So I know that the radius is half the diameter, so I can rewrite that equation up there. Area equals pi times the radius, but radius is half the diameter squared. So the area is pi times what? Square that. What do you get? 1/4 d squared. Remember, to square something in parentheses, you must square both factors, right? So you square the 1/2, right? 1/2 times 1/2 is 1/4. D squared is d squared. And so I would probably write something like this. Area as a function of diameter is equal to 1/4 pi d squared. The key to this problem and to the next ones is that you have two variables you're trying to connect, and you have to use your knowledge of geometry in order to connect them. The thing that we had to know here was, first of all, area of a circle is pi r squared. And the next thing we had to know is that the radius is always half the diameter. But let's look at the next example and see what it is we're going to have to know. Express the volume of a cube. Wait, volume of a cube? volume of, oh wow, volume of a cube as a function of its surface area? Okay. So what is a cube? Yeah, it's six-sided. It's like, you know, all equal sides. So like a die, right? A dice, right? Isn't singular die? Okay. So I have a die. How do you draw a die? There's the front, goes back, comes down. Oops, I don't like that. Okay, so there's my cube. All the lengths of all sides are equal, right? So let's label some sides. I heard X. That sound okay with you? X, that means this is X, and that means this is X. And I know the volume of that is what? What's the volume of a cube? X times X times X. So X cubed. That I know. Now, do you know anything about the surface area? Okay, now I'm going to write A instead of, for surface area, I should do like SA or something. I'm just going to write A. Is everyone okay that that's going to mean the area, the surface area? The area is, okay, so tell me the area of just this front side right here. The area of that is X squared, isn't it? And how many sides are there? 6. So shouldn't the area be 6X squared? So what I need now is a final formula that gives me the volume as a function of what, though? Surface area. I need to somehow connect the volume and the surface area together. So how are you going to do that? Everyone understand the question, what we're trying to do? What do both the volume and the surface area formulas have in them? They both have an X, right? So why don't we try and solve the area formula for X? Take that answer and stick it right here for X. So I'm going to take this right here and solve it for X. How could I solve that for X? What would be the first thing you could do? Divide by 6. Now, I'm not going to divide. I mean, I'm going to divide, but I'm not going to write A over 6. I'm going to write 1/6 A equals X squared. Is that okay? Now what? Square root, right? And when you take the square root, what do you always have to do when you take the square root on both sides of an equation? You always have to do plus or minus, right? However, in this problem, do we need to look at negative? Why not? Because X can't be negative, right? X is the length of the side of a cube. So it's negative. I don't need to consider it. Y'all agree with that? Now, just for the sake of understanding radicals, do you agree with this? The square root is the same as raising something to the 1/2. Now, let me come back and I'll do it in red here below this. What did we say the volume was? It was X cubed. But now the volume is actually, what was X? It's 1/6 A to the 1/2. But then what are you going to do with that? Cube it, right? Y'all see what I did there? And what do you have when you have something to a power to another power? What do you do to these powers? You multiply them. So our volume is actually 1/6 A raised to the 3/2. And that is a pretty clean formula right there. If somebody gives me the area of a cube, I can take 1/6 of it, and I can raise it to the 3/2. What does it mean to raise something to the 3/2? You cube it, and then you take its square root. That's what that means. You can also do it the other way. You can take the square root first, then cube it. But I'd say that's a good formula, right? The only thing left to do would be maybe write V of A equals 1/6 A to the 3/2. That's just writing it as a function, okay? Like f of x, I'm writing it V of A. All right. Why don't you try the next one on your own? Or you can talk amongst each other in groups. And as soon as your table all comes to an agreement, you can take that first break. You need the notes? I think that's. You're trying to express the surface area of a sphere as a function of its volume. This one's a tough one. Anyone have a book with them? Because you might need to know these formulas. Because these are spheres, right? Would y'all like the formulas? I'll give you the formulas just to cut down on time for you. Okay? All right, so for a sphere, the surface, well, we'll do volume first. Volume is 4/3 pi r cubed. The area of a sphere is 4 pi r squared. Okay, see if you can express the surface area as a function of its volume. So you want A of V equals what? All right, we are back in business now. Just remember, if you came in a little late, I already assigned the quiz that's due next class, right? So if you weren't here when I announced that, just check with me after class. I'll tell you what the quiz is. Any other questions on this problem? All right, we're going to move on to the next set of notes. So, are there any extra notes laying around? There's some right there. Sir, did you just walk in? Did you just walk in? Okay. Thank you. So we're going to start 1.2. My goal today is to get through the first 3 sections, so let's see how this goes. We're going to talk about a catalog of functions. So these are kind of like functions you should know coming into this class. And I'm going to turn off one more set of lights so we can see this. Functions you should already have had some experience with. First of all, the power functions. I think I'll try and blow this up just a little bit. Power functions like x squared, x cubed, x to the 4th, 5th, 6th. All of these functions have 0 as an x-intercept, right? If I plug in 0, I get 0. And what else can we say? How about this one? This is like a parabola, right? Both sides go up. Cubic, what's going to change? It'll be down on the left and up on the right instead. What will x to the fourth be? No? Kind of like a parabola, except it'll be a little steeper and it'll go up a little faster here on both sides than there's the parabola next to it. The red one's the parabola, the green one's the fourth degree. Also notice this, like the parabola is above x to the fourth between 0 and 1. How about x to the sixth? Even steeper than x to the fourth. And then there's x to the fifth and x cubed. Let me take the even ones out, just look at the odd ones. So those are just your basic power functions. Negative power functions. So x to the negative 1. X to the negative 1 is the same as 1 over x. Hard to see that. Right? X to the negative 1 is the same as 1 over x. There's 1 over x. That's a rational function. X to the negative 2 is 1 over x squared. I like to call this the volcano function. Right? It looks like kind of like a volcano. Both sides go up in the middle. They keep going up to infinity though, right? What's happening at 0 for both of these functions so far? What's happening at 0? That's right. You have something, we call that a what? When a function does that at, what do we call that? You remember? Asymptote, vertical asymptote. Has a vertical asymptote at 0 because if you try plugging 0 in, it's undefined. So we have asymptote, here's x to the negative 3, which is the same as 1 over x cubed. X to the negative 4, it's like a volcano again. X to the negative 5. All of these have that weird thing happening at 0 though, right? They also have another property. What's happening to all of these functions as you go out to the right or to the left? They're all getting closer to 0, right? They're all getting closer to the x-axis. We call that a horizontal asymptote. Root functions. That's square root of x. Right, that's the function, square root of x. Kind of looks like a parabola. It's been laid on its side, cut in half. How about cube root? What's going to be different when I put cube root in here? I'll have negative values because you can take cube roots of negative numbers, right? So it's going to look like that. How about a fourth root? Should I have negatives? No. So it looks very much like the square root. Fifth root, that'll have negatives. Sixth root, no negatives. All right, so that's the basic behavior of root functions. Oh, polynomials, geez. This is a huge category of functions, polynomial functions. Lines are examples of polynomials. F of x equals x. That's a line, right? What happens if I change it to f of x equals 2x? What's going to happen? Instead of x, 2 in front. What would happen to this? It'll get steeper. What happens if I change it to 10x? Steeper. Could I ever get it straight up and down? A vertical line is not a function. So it'd be impossible. Okay? I guess what I'm trying to get at here is, what if the number I put in front, like right now it's 10, what if it was 100? It would be even steeper, right? What if it was 1,000? Even steeper. What if it was 1 billion? Even steeper. But you can never get it vertical. It's impossible. The bigger the number in front, the steeper it gets, but you just approach vertical, but you never get there. All right. Now that's just a line. That's an example of a polynomial. This is what we call a degree 1 polynomial, because the The power on the x is 1. Now what if I make the number in front here a negative number? What's going to happen? It's going to slope the other way, right? And then again, -2, -3, -4. The bigger I get negative, the steeper it gets that direction. But I can never get vertical. So those were lines. All lines are examples of polynomials. Now what if I make it instead of a degree 1, and so instead of x, I make it x squared? Now it's a parabola, isn't it? And I could have parabolas that look like that. Maybe I could do something like this. So now I have two x-intercepts, 0 and 3. I can flip it over by changing the number in front of the x squared, making it negative. Now it opens down, right? So quadratic functions, parabolas, are examples of polynomials. But you can keep going, right? Polynomials, you can go higher and higher degrees. There's a third degree polynomial. Changing the scale on the graph so you can see that a little better. I can do separate x-intercepts there. That's third degree. I can change the numbers to make it flip the other direction. These are all college algebra topics, polynomial functions. The thing about polynomials, though, is they're always nice and smooth, aren't they? Like, there's no like crazy breaks in the graph. And for degree 2 and higher, they're always curved. Like lines are just lines, right? But from degree 2 and on, you get curves. Watch, I'll go a degree 6 polynomial here. And I'll throw in a bunch of different roots. Let me do one more here. Let me scale this out so we can see it. See if I can get this to come in. I may not be able to get it all in here. Not quite. Can't get it all in there. But it goes down, then it comes up, and then it comes back down and up, and then back down, and then back up. Right? So everyone comfortable at least with the idea of what polynomials look like? Rational functions. Again, rational functions are a college algebra topic. Rational functions are defined to be a polynomial divided by a polynomial. So if you divide two polynomials, you get a rational function. And they have these things called vertical asymptotes, where the function takes off, gets all crazy. This is another thing you can play with here. Change the degrees, change different values. This is the function right here. It's graphing. Okay, so rational functions usually have vertical asymptotes and horizontal asymptotes. We're not going to do a full-blown study of these, just as long as you've seen them, good. Trig functions, that is the classic sine function right there, right? Cosine, looks like that. Tangent, what does tangent have that sine and cosine don't have? Has asymptotes. Does anyone know where the asymptotes for tangent are? Yep, it goes, there's like this vertical, where is it though? Does anyone remember? There's two like classic ones everyone should remember. Pi over 2 and negative pi over 2, good. There's tangent, the blue. Let me take sine and cosine out of here. Hey, what is tangent? In terms of sine and cosine, what's tangent? Sine over cosine, right? So if tangent is sine over cosine, then every time cosine is 0, shouldn't you have something division by 0? Every time cosine is 0, shouldn't you have division by 0 for tangent? Do I need to write that down? Here's what I'm trying to say. If tangent x is sine x, over cosine x, then whenever cosine is 0, you should have division by 0, right? Which should cause a problem, shouldn't it? So let me go back to that graph, and let me bring cosine in here. Look at where cosine is 0. Look at where cosine is 0, right here, right? And what's happening to my blue function at that point? I have my asymptote. And every time cosine hits 0 again, that's where I create asymptotes for the tangent function. Yes? So then what about cosecant then? What is cosecant by definition? 1 over sine. So where should cosecant go crazy? Wherever sine is 0, which would be, here's sine. I put sine back up here for you. Where is it going? Where is sine 0? 0, pi, 2 pi. So if I pop cosecant in here, shouldn't I have asymptotes there? And then this is cosecant up here. Cosecant, cosecant, that part. Do I remember graphing cosecant and secant and stuff in pre-cal? It's been probably forever, but okay. What about secant? Secant we said was 1 over cosine. So let me take sine out of there and put cosine back in. Let me throw secant in there. I should have problems wherever cosine crosses the x-axis. Take cosecant out. So there it is. Wherever cosine crosses the x-axis, I have an asymptote. So it's this black function right here. Last one, cotangent. What's cotangent by definition? 1 over tangent, but in terms of sine and cosine, what is it? Cosine over sine. So everywhere sine is 0, so let me put sine, I should have a problem. So here's cotangent. So again, sine is 0 here, I have a vertical. Sine 0 here, I have vertical. Take that out. That's your cotangent. Okay. Remember, these go on, right? These repeat. So like any of these, you could put them up there and they just, the periods, they just keep on repeating themselves in both directions forever. Exponential functions. What is an exponential function? It keeps growing, but what is it? I mean, like, that would be an example of when we would use them, yes. But what is it? Like, all exponential functions are some number, a, raised to the x. So like 2 to the x, 3 to the x, 1/2 to the x, 10 to the x. E to the x is a very special one, isn't it? We called it the natural exponential function. But what we have with exponential functions is that our variable is the power, right? As opposed to polynomial functions where the base is the variable. So here's e to the x, one of the most important functions in mathematics right there. Here's 2 to the x. Here's 1/2 to the x. So those are all exponentials. What are the log functions? They're the inverses of the exponential functions. So if I take e to the x and I show you natural log x, it should be its inverse. So when I graph it, it should be a reflection over the identity. Here's the identity line. Here's e to the x. Reflect e to the x over that dotted line, and you get the natural log. That's the property of being inverses. If I do the 2 to the x function, the inverse of that is log base 2. So that's its inverse. I'll take the e out of there. You see those two are reflections also. If I do the 1/2 to the x, then its inverse should be a reflection of it. Right there. Log base 1/2. All right, now, knowing that, well, the fact that we've studied all those somewhere in the past, whether it be last semester or 20 years ago, we should all have some background with those functions. Now, transformations. If you know a function, okay, you're given a graph, you know what it looks like, then we can move it around pretty easily. If you take that function and you add a number to it, it moves it up. If you subtract a number, it moves it down. If you add a number inside the function, it moves you left. If you subtract a number inside, it moves you right. And you have to be careful with these, because these two right here are bass-ackwards, right? You know what I'm saying? They're opposite of what you think. I mean, adding C moves you up, subtracting C moves you down. That makes sense. Up, positive, down, negative. But for left and right, it's opposite of what you think. Adding doesn't move you to the right, adding moves you to the left. Subtracting doesn't move you to the left, moves you to the right. Then we can shrink and stretch graphs by putting numbers in front. So if you put a number, a constant, in front of a function, then it will stretch it vertically by a factor of C when C is positive. If you put a number in front that's smaller than 1, like a fraction, like 1/5, it'll shrink it vertically. If you put a constant inside, then it'll shrink it horizontally or stretch it horizontally depending on the number inside. Then there's reflections. You can reflect over the x-axis and over the y-axis by putting negatives. So these are all things, again, in college algebra you should have done transformations. The only thing different right now is that we're talking about transformations on everything we've studied instead of just like trig functions or parabolas. So let's look at this one right here. That is a quadratic function right there, parabola, right? That's just x squared. So right here, it's kind of hard to see that. Let me change this a little. See how this says 1 and then 1 plus x, or sorry, 1 times x plus 0 squared plus 0. Isn't this just 1x in here? So isn't that just x? Isn't that just x squared? Times 1 is x squared, plus nothing is x squared. So this is just x squared, right? So let me move it up. That would be a vertical shift, right? If I want to move it up, what would I do? So add some number to it, like let's say 2. So it should be a plus 2 right here now. And that's what it would do, right? It would move that whole graph up too. What if I had done down 1 right there, right? So this changing this number out here moves it up and down. Now let me change the number inside. So what would I do in order to move it to the left by 1? If I want to move this one right here to the left by 1, I would add 1, right? So I put a plus 1 inside. Plus 1 inside moves me to the left 1. What if I wanted to flip it over? Change it to right here in the front. Flip it over the x-axis. Change it to a what? -1? Let's see. I may not have -1 there. Yep, there we go. -1. See, it's a -1 there. What if I put -2? What would it do? Instead of -1. It would still go down, right? But it would be narrow, right? It would stretch it out, shrink it. We would call that a compression or like a stretching or shrinking horizontally. I mean, there's different ways to say it. All I want you to do is, like I said earlier in class, if you download that player and you come in here at home, you can mess with all this and just see how changing numbers affects graphs, right? All I'm doing right now is messing with the quadratic, though. I mean, we could do the same thing for sine, right? Take the whole sine function. Let's move it up 1. Let's move it up a half there, right? Let's move it to the, let's see, if I put -pi/2, it's going to move it to the right by pi/2. Right, I can flip it over. What did I do there? Did I just do that right there? See. Oh, I changed that. That changes your period. I didn't. This is wrong. Shouldn't say horizontal shift. It should be period. Let's see. Flip it over. So you can play with this on your own. Combining functions. Again, this is a college algebra topic. There are 4 operations that we learned in college algebra. If someone gives you 2 functions, right? F of x is this, g of x is this. You can do 4 arithmetic operations. You can add the 2 functions together, subtract them, multiply them, and divide them. But there was a fifth operation with functions. Do y'all remember it? Remember the fog? It's called functional composition. What's the difference between those first four arithmetic combinations and composition? What's the major, like, I mean, there's a fundamental difference between the two. What? Yeah, it's a function inside of another function. It's a function plugged into another function instead of a function plus another one multiplied. So you can have f go into g or g go into f. Like in this one right here, which function is going into which function? G is going into f. What if I wanted it the other way around? It would be called goff. It would be g of f of x. Okay, so that's our operation. Now, let's see how we're going to do this in this class. So it's time to do some examples. So I'll do these on my page here. You'll notice how I'm kind of talking through these notes, right? And I said we've got those pre-class videos. That's basically what I'm doing, is I'm going through them, talking like I am now. If you watch that before you come to class, then all I'm going to do are the examples. And we will be able to do a tremendous amount of problems in this class if you do your part. If you walk in here and you don't watch any of it, you're going to suffer for that, because you're going to be like, I don't know what he's talking about. You know what I'm saying? The biggest thing I think in Cal 1 is you need to see as much as you possibly can, because there's so many tricks, there's so much algebra involved in this stuff that we don't have time to sit there and spend on me walking through this every class. All right? All right, let's get to these examples. I give you two functions. They are f of x equals x squared plus 1, and g of x equals x minus x squared. So let's find this first thing, f plus g of x. So what do you do when you see that? So you just add them, right? X squared plus 1, add to that what? Plus the other one, x minus x squared. And now you just combine like terms. So what would you get? Careful. Just x plus 1, right? The x squareds cancel. Now, what if we do f minus g? Subtract. So there's one thing we do have to be careful with here. What's that? That negative is actually going to have to distribute, right? So I should put the x minus x squared in parentheses so that I can distribute that negative through. So that becomes x squared plus 1 minus x plus x squared. By the way, we're reviewing right now. Have you all kind of picked up on that? Okay. So 2x squared minus x plus 1. Is it wrong if you would have written it, 2x squared plus 1 minus x? No, it's just we like to do things in descending order, but it's not incorrect to do it another way. All right, next one, fg. So f next to g like this is implied what? Multiplication. Bless you. So you need to put the x squared plus 1 times, in parentheses, the x minus x squared. And what do we call that when you do that thing? When you multiply two things like that together? What do you call that? When you go like from here to here, and then here to here, here to here, and here to here. Foiling is the cute name for it. What's the proper technical name for it? Expanding. It's called expanding. All right, so we're expanding these binomials. So x squared times x is x cubed, right? X squared times negative x squared is negative x to the 4th plus x minus x squared. Oh, we don't even have any like terms, do we? So I could leave it like that, or I could put it in descending order. I'm just going to leave it. What about division? What's that? The last one is 1 times negative x squared. So the next one, f over g, I think hopefully that's obvious that that's just division, right? X squared, or x squared plus 1 over x minus x squared. Now there's not a whole lot you can do with that, okay? There's not a whole lot you can do with it. So we could leave it like that. But I want to bring something up because, you know, so many of you said you're going to have to take Cal 2. I want to show you that you could divide these two. I'm going to change the order here. Just flip the bottom around, okay? How can you divide two polynomials? You use long division. X squared, 1. Now, I left a gap in here. Why did I leave a gap? I don't have an x, right? So I just left a gap for any x terms. So that's x squared plus 1. I'm dividing that by what? Negative x squared plus x. How many of you have seen long division before? It's just been forever, right? Okay, so what you do when you have long division is you look at the first term here. Now everything has to be in descending order, which it is. And you ask yourself, what do you multiply negative x squared by to get positive x squared? Negative 1. So I'm going to put, and it doesn't really matter where you put it. Some people like to teach it where like you line it up, like, you know, if your x squareds are here, your x's are here, then, you know, 1 is here. So what were we going to multiply by? Negative 1? You put negative 1 on top of the negative. That's not necessary, but you can do it that way. What's negative 1 times negative x squared? X squared, so you put that here. What the hell? Negative 1 times x is, so negative 1 times x is negative x, so I put that right here. And that's it. Now I come through here, and what do you do with this? Subtract it. So that changes the signs. It makes this minus x squared, and it makes this plus x, doesn't it? And then go and add down. What would you get? X squareds cancel, right? Just x plus 1, right? And now you ask yourself, what do I multiply negative x squared by to get x? And that's where you stop. As soon as the power on the outside is higher than the power here, on this x down on the bottom there, as soon as that power out here is bigger than that, you're done. So this is our remainder, isn't it? That's what's left over. So the way you write that is like this, up on the top, plus your remainder over your divisor. That's it. Now, you might be saying, why in the hell would I want to do that? Well, take Cal 2, and yeah, you'll see. Where were we? I kind of got sidetracked there. Now we want to do fog. F of g of x. So this means we're going to take the f function and we're going to plug in the g function. That's the definition of composition, right? So I'm going to put f, and inside of f, I'm putting the g function. What's the g function? X minus x squared. So that's going to be plugged into f. So everywhere I look at the f function, and everywhere in the f function that I see an x, I replace it with that, right? So it becomes what? x minus x squared squared, then plus 1. And then you'd have to multiply that out. What's x minus x squared squared? Is that x squared minus x to the 4th? No. You have to FOIL it, right? Could you FOIL that on your own? Good. Should become x squared minus 2x cubed, I think, plus x to the 4th plus 1. Pretty sure that's what it is. Now, how many of you were taught fog and Goff? No? Fog and Goff, that cute little, okay. How about this, though? What would g of f of g be? I mean, there's nothing saying that you can't have composition repeated. This would mean g goes inside, well, we have g inside of, let's see, f inside of that is g of x. So we had g, g, f, g. So g, g, f, g. So g goes inside of what first? F. That answer goes inside of g, and that answer goes inside of g. Okay, that's a bonus. You can turn that in next class. All right? It's tedious algebra in there. But put that all together and expand it all out and turn it in for bonus if you like bonus. It's just to show you that you can have functions composed with themselves and with other functions. All right, let's now not do 1.2.6 because of time. Let's go on to note 1.2.7. What we're interested in this class is not what we were just doing. That was just to kind of remind us how to do the algebra and arithmetic. What we want to be able to do is called decompose a function. So I'm starting out with this function m, capital M, of x equals sine to the 5th x squared plus x. All right. So the instructions are find the functions f, g, and h such that m of x equals f of g of h of x. So we want to find f of x, g of x, and h of x. So we're actually working backwards. Somehow this capital M function is a function inside of a function inside of a function. So what are they? Do you all see 3 functions here? What are the 3 functions that you see in this, if you even do? Sine of something is a function? Say again? Sine would be, well, before we get to which one is which, let's talk about the functions that you do see. You see sine of something, what else? X squared plus 1 is a polynomial function. What else do you see? What does that little 5 mean? Doesn't that mean raise it to the 5th power? Doesn't having a 5 right here on this sign mean raise that whole answer to the 5th? So this really means, like, imagine that you were x, okay? What's the first thing that would happen to you if I plugged you into this? You get squared. Then get added to 1, and then, well, take sign of it, right? So then you take sign of that, and then finally raised to the 5th power. So if we're looking at functions here and we're trying to decompose this, there's two ways to look at it. You start from the outside and work your way in, or you go from the inside and work your way out. We, because of where we're going, are going to start from the outside in. So we want to start from the last thing happening and go to the first thing happening. So what's the last thing that would happen in this problem? Raised to the 5th. So I'm going to put here for f, x raised to the 5th. So now I'm going to kind of scratch out the 5th power. What would be the next thing as we went in? Sine of something, right? So sine of x. So now I'm going to scratch out the sine. Now what? X squared plus 1. So how would we check it? We take h, right, and plug it into sine of x. So I'd plug it into g, right? And that would give me, well, I'm trying to jump too far. Let me write down over here, f of g of h of x. This right here, f of g of h of x is this, f of g of h of x. H of x goes in here, so it becomes f of g. I'm just checking right now, right? H of x is x squared plus 1. Take x squared plus 1 and plug it into g. What would you get? Sine of x squared plus 1. And now take that and plug that into f. Sine of that, all raised to the 5th, right? So I just put the 5 there. So that checks. It depends. I think you're asking me this. Is this sine of x squared plus 1? I don't know why I'm having so many issues with my writing here. Did y'all see that warning pop up earlier about changing my color scheme? I should have changed it because I think my computer is running at like maximum performance right now. Let me see. Where is it? Performance. That's not so bad. It's peaking out the certain spots. Okay. Okay, so the question was, is this correct? Well, what do y'all think? What's wrong with this version? Yeah, this would mean x gets squared first, then what? Plus 1, then raised to the 5th, then sine. So that would not give you the same result. To make that correct, you would need this to be in brackets or parentheses. You can do either one. Okay? Good question. That's why we put the 5 here, is so you realize that that's the last thing happening in that problem. Well, in this particular one. All right, that's it for those notes, but I want to see if you can do one on your own here, okay? Or with each other. So I'm going to give you a capital M, and I want you to try and break this down. Capital M of x equals fourth root tangent sine square root x plus x. Find f, g, h, and k such that m of x equals f of g of h of k of x. So I'm telling you that there's a function inside of a function, inside of a function, inside of a function. 4 of them. Can you determine what they are? Remember I said work your way from the last thing happening back to the first. Or work your way from outside in. Okay, go ahead. I just realized I didn't record that last thing that I did over here with the U, V, W, T. So, oops. If you have it and you want to ask, want me to come by and take a look, I will. Or if you have a question. So you got it in, what, 4? All right. You can go one more. Yeah. Oh, and try and do it with the way I did it with UVW also. So you can do it either just the UVW type way or both. But I want to make sure you can do the one on the right instead. So T. Yes. So you're saying it would go like from here to here and then here to there. Okay. Opposite. That's fine. However, you can go one more. There's still another one in there you could do. You have one more, maybe. See if you can convince yourself. There we go. U is V, V is T. Tangent S. Good. Good. That's what I'm looking for. Any progress? Did I check y'all on the last question, or did I skip over you? Did I come by? I did? Okay. Okay. Oh, I'll give you more time. Okay. 3 over G. G is 5th root of H. H is J squared. J is tan K. K is M plus 1. Yeah, that'll work. That'll work. Yeah, you went even further. Now the last one is this right here to here is good, but it'll be overkill later for that because you would be at a polynomial right here, even if you said m squared plus 1, and once you're at a polynomial, it'll be easy. Like later, we'll be happy. Okay, so he's got it. Yeah, 3 there. Yeah, so you got it down to what, 5 of them? Okay, now try and do it with the letters like U, V, W type thing. R is cube root. 5th root. 5th root. You got to be a little careful here. Hold on. Yeah, you're good. You're good. Well, no, there's a problem here because you're done with the 5th root, right? So what's the next thing happening after? Like if you go inside the 5th root, what would be? That is. Well, if I write down this, if I write tan squared of what is it, x squared plus 1, this means tangent of x squared plus 1 squared. Yeah, well, anytime you have this, that's what it means. So if you were looking at working from the inside out, it would be this, then tangent, then square. So coming back in, it would be square, then tangent, then this. Yes, that's right. Did you? Okay. Yes, that's right. Good. Yes, that's it. Anyone here? 3 over S. Oh, well, yeah, you could do it that way too. S is this. That's that. That's that. That's that. That's that. So you have 1, 2, 5. There seems like, hold on, it just seems like there's something missing. You have 1, 2, 3, 4, 5, 6. Yes, okay. That'll work. It's not the only way, but that'll work. Okay. Got to be careful on this. Take a look at this again. There's a little bit of an issue here. Anything here? Did I already look at yours? You were good? Fifth root. This is where we have an issue, because if you look at this, the fifth root happens, right? The next thing inside that happens is a squared. So you would need this to be a squared and then tangent on your next function in. I'm going to work through it right now in just a second. So this is right. That's right. Okay, I'm going to work this one out on the board real quick, just to see there's different variations of this. The way that I would look at this is that, again, I'm going to start from the inside, work out, and then back in, okay? If I'm x, the first thing that happens to me is I get squared, then plus 1, right? X squared plus 1. Then what would happen after that? Does the tangent happen or the squared? Tangent. Okay, so tangent would happen next, then squared, then fifth root, then 3 over that, right? So I think I'll start off with u is equal to 3 over something, v. All right? Now, what's v? It's the fifth root of something, w. Okay, what was w? It's something squared, right? T, whatever you want. I'm going to use q just to show you. You can use whatever letters you want. Q squared. What's q? Tangent of z. What's z? X squared plus 1. Now, you could even go further than this. There are little subtle things you could do at the end, but this is breaking it down. Where look at every function we have here. 3 over v, to compare it to something, is like 3 over x. That's a rational function. It's a power function. This one right here, this is a root function, isn't it? So this is a power. This is a root. This next one is a power function, right? This next one, tangent x, is a trig function, right? And then this last one is a polynomial, right? And what we're going to be doing later is we're going to take some nasty thing like this up here, and we're going to be trying to figure out what its derivative is. And you don't really know what that means yet, but to do that, instead of trying to attack this big, ugly, nasty thing, you're going to break it down, and you're going to do the derivative of a power, of a root, a power, a trig, and a poly. And those will be easy to do. And then you somehow combine the answers together. But you got to be able to break it down. All right. We still have half an hour. To me now, this is actually where the class begins. So are y'all okay? I mean, can I keep going? Have I lost you? Is your attention all gone? You still there? Everyone has the notes for these? Let's see how far we can get with this. I'm going to try and stop myself in 20 minutes because I want to just kind of recap what you need to do, and when you go home, like what's homework, like All right, so in the past, I've been known to actually start a class first day in 1.3. But I've done a little review for us. All the things we've done are just kind of, they'll pop up here and there. This is where calculus begins, though, for me. It's everything in calculus, in Cal 1, Cal 2, Cal 3. Everything is born from the idea of the limit. All right? So what we're going to do to begin is look at, and I don't think you have any of this on the notes. Whoa, 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 whoa. It says, discuss the behavior of this function around the value x equals 2. I think I'm going to kill the light so we can see that a little better. So let's take our time through this because, like I said, this is the most important thing in calculus, is understanding the idea of a limit. So here's our function right here. It's what type of function? Power would be just an x by itself. Polynomial. So if we combine power functions together, we get polynomials. Well, it's a negative power. That's the same as 3 times v to the negative 1. But you could also say it's a quotient or a rational function. Either way. Okay, so what is happening? Discuss the behavior of this function around, okay, that's the key word, around the value x equals 2. So here's x is 2, right? If I go up here on my function, what does it look like my function is close to? It looks like it's close to 8, doesn't it? That looks like about 8. And so what I can do here is I can slide around. I think I can slide around. I should show it, huh? There we go. There we go. So look what's happening. I have here on the x-axis my x value, which right now is what? 1.4. And then this right here is my y value. That's what's coming out. And right now it's about what? 5.096. So as I get closer and closer to 2, closer and closer, right? What does it look like I'm getting closer to? 8, right? Now, when I was sliding this, you see how these jumps I had getting closer were pretty big? Like, look, I go 1.3. What's the next one? 1.4. Next one. 1.5. 1.6. 1.7. Right? I'm jumping by a tenth every time. Right? So you see this right here? I can change it to a slower jump. So now, when I jump, it's going to be 1.71, 72, 73. See how I'm going a lot slower to it? Now look at my y value, 7.4, 7.7, 7.9, 7. Right? Now I can go to 1/1000th. Now I'm 1.991, 1.992, 1.993, and look at my y value. Getting really, really close to what? 8. The limit is not asking you what is happening at 2. Okay? What you want to almost imagine is that the best analogy I ever had of this is when we've looked at a function in the past, right? And we say, oh, plug in 2. All you did was go to 2, right? Plug in a value, and you get that value, right? And so you basically said, cover up everything in the graph, who cares, and tell me what's happening at 2, right? The limit is backwards from that. The limit says, you don't get to look at 2. Hide that, okay? And look at what's happening right next to it. So the analogy that I was given was like a window. Here's a window. That's like the wood frame of the window. And you have like a shutter, and you open the shutter, and you can't see what's happening right down the middle. Okay, so there's my shutter. Can't really see what's happening in the middle because the wood's covering it. But what's happening on the outside is what you're looking at. Does that make any sense? Okay, so that's what's happening as I was coming in from the left, right? As I came in from the left, the closer I got to 2, the closer this got to 8. Now, will the same thing happen if I come in from the right? So now I'm going to pull in a point from the right side. Now, I'm pretty far away from 2 right now, aren't I? So let me get close. So right about here. And it went up. Now it's coming back down. Look at my x value. I'm going to take the other one out of there so it doesn't get in the way. So I'm close to 2, right? 2.3. Let me get even closer. 2.2, 2.1. That's close. What's my y value? 8.4. So as I get closer, it's getting closer to 8, right? But now it's a little bigger than 8. So when I came in from the left, it was a little smaller than 8, getting close to 8. Coming in from the right side, it's a little bigger than 8, but it's still getting close to 8, right? Getting closer and closer and closer. Oh, I went too far. There we go. Pretty damn close. So it would appear, right? The appearance is that if I come in from the left or from the right, it appears that the function is approaching what? 8. So at 2, the function's value is 8. Compare that to this. Now that's a piecewise function. What's happening at 2? At 2, what's the function's value? What's that? Well, it has to be at 2. Like if I tell you plug 2 in, everyone take 2, plug it into this function, what would you get? You'd get 8, right? Because I have a solid dot up here. But that's not calculus. That's college algebra. Now we want to close off the middle where you can't look at this anymore, and I want you to look at just the outsides as you come into it. So let me come in from the left first. So I'm going to approach here, moving 1/10 at a time. What does it look like it's approaching here? It looks like it's approaching 8, right? And I could go smaller steps, and I think you'd still be convinced that it's getting closer and closer to 8 as I come in from the left, right? 7.96, 7.97, 7.98. I'm getting really darn close to 8. I would say from the left it's approaching 8. But from the right, is it approaching 8? Yeah, look at this right here. See, I'm coming in. Come on. Come on, there you are. So what is it right now? 4.6, 5, 5.2. So I went up. I'm up at 5. So am I approaching 5? No. Let me get closer to 2. Where's it headed now? Take this one out. It's headed towards smaller steps here. 4.34, 4.3. So smaller and smaller steps, getting closer and closer to 2. Keep going, get closer and closer and closer and closer. The y value is approaching close to 4, right? So from the left it was 8, from the right it was 4. You see the difference though? Major difference. So let's try and recap this. In the previous problem, what was happening as I came in from the left? Where was it approaching? As I came in from the right? 8. What was happening at 2? What was f of 2? 8. So from the left it was 8, from the right it was 8, and at 2 it was 8. That's like great. Everything was trying to behave well. This one, from the left it was 8, from the right it was 4, and at 2 it was 8. All right? How about this one? What is it from the left? Where is it headed? Up to 8, right? Where is it headed from the right? It's approaching 4. Where is it at 2? 6. So from the left it's 8, from the right it's 4, but at 2, college algebra at 2, you get 6. Look at this one around 2. We're looking at 2, not negative 2. Well, hold on. Let me read the instructions. Discuss the behavior's function around 2. Kind of hard to see it. This is 2 right here. What's happening? From the left, well, there's an asymptote way over there, but that's not close to 2, right? Over here is -2. I'm not concerned about that. It's what's happening over here. So where is it getting close to? Well, I'd have to keep getting closer, right? 1.7, 1.8, 1.9. Let me get even closer. 1.91. What does it look like that's headed towards? What's the value? Is that straining your eyes too much looking at this? It's straining the hell out of my eyes. Y'all are all right? What is it? -2.5 it looks like? Or -0.25. -0.25 from the left. And then from the right, what's happening? Oh, little problem with my code there. Where's it going? Same thing, right? About -0.25. Did y'all see that? What's happening at 2? What's happening at 2? It's undefined. Look at the function up here. What happens if you try and plug 2 in here? You get 0. You get division by 0. But actually, this is a hole in the graph, not an asymptote. So look at this one. You come in from the left, it goes to -0.25. You come in to the right, -0.25. But at 2, college algebra at 2, undefined. Right? Okay, discuss the behavior of this function around 0. This is a very interesting function, sine x over x. We're going to look at that more. What happens as I come in from the left? Where does it look like it's headed? Looks like it's headed towards 1, right? Where is it going as I come in from the right? Headed up to 1 also, right? But what's happening at 0? At 0, what does it look like is there? A hole. Again, what's sine of 0? 0 divided by 0, you get undefined. So our function should have a hole in it. Do you think you're getting the idea? Sine of 1 over x. Oh, wow. Okay. Let's see what happens here. Here I am. Life is good. Just do. And all of a sudden, all hell breaks loose here. Okay, I'm going to go in slow to this. So what happens is, as I move, maybe I go a little faster. I'm up. Where am I headed? 1, and then where am I headed? -1, and then back up to 1, and then holy shit, the walls are caving in here, right? And actually, let me zoom in a little bit so you can really see in here. It's just frickin' chaos in there because all I'm doing is I'm oscillating. And see how it's starting to look real jagged? That's just the limitations of the computer itself, okay? That's not because the graph becomes jagged. What's happening is this is oscillating infinitely many times as you get closer to 0. That's how you would prove where it's going later. But this is it. The question, I guess, becomes as I start moving in here, it goes up and then it goes back down and then back up and then back down and then back up and down and up and down and up and down, and it's going crazy. Is it headed somewhere? Is it headed to one place, one numerical value? No, it just keeps going back and forth. So everything we've had up to this point is you come in from the left, it was headed somewhere, right? Coming from the right, it was headed somewhere. This is our first example where the function actually doesn't head anywhere. It's oscillating infinitely. So we will say here later that this does not exist. Like this left hand approaching is not approaching anything. Okay? Same thing's happening from the right side. Try and come in from the right. There it is, all nice. Oh, whoa, whoa. And now going up. Where is it? Did I lose it? Well, there, it's up. and down. May not have gone far enough. Let me go a little closer. There it is. I was looking for the dot. There, now it's up and down, up and down, up and down, up and down. So it's oscillating. So what I say here is from the left, the function's values appear to be approaching oscillating. What? To be oscillating is what that should say. And from the right, the function's values appear to be oscillating. At 0, the function's value is undefined. Again, because you get division by 0. Does that make, do you all understand that picture? I mean, that's an important graph there. Look at this one. What's happening around 0? Okay, we have an asymptote, but approach from the left. Where am I headed? I'm headed down to negative infinity. Here I go. I'm off. See you later. Right? It's taken off. It's going to go off my screen. And the closer I get, right? The closer I get to 0, the bigger negative I get. Look at that. I'm at negative 125, negative 142, negative 1,000, right? Could I get closer than 0.001? I go to 0.00001, right? Or 0.00001, or 0.00001, right? Or I could have a million zeros and a 1, right? So I can keep getting closer. That number's going to get bigger. So that's headed to negative infinity. What's happening as I come in from the right? It's going positive infinity. There it goes. Oop. When I do that and it turns red, that means my computer is trying to divide by 0. And so it's not happy. So from the left, it appears to be approaching negative infinity. From the right, it appears to be approaching positive infinity. And what's happening? College algebra question. At 0, undefined. 1 divided by 0 is undefined. Look at this one. Where's this one headed? From the left, where's it headed? Now we're approaching 0 again. To the left, it's headed to positive infinity. From the right, it's headed to positive infinity again. And what's happening at 0? Undefined. So infinity, positive infinity on the left, positive infinity on the right, undefined at 0. All right, that is all the pictures. Everything else is going to be where we start talking about definition. So I think this is a good place for us to stop, I guess, and talk about a couple of other things, like homework, what it is that I want you to do. I don't want to overload everyone with like I said, all these files and videos and everything like that, but I like to provide things to students who are willing to look at them. So all these things that I've been doing today, all these little things, all this stuff, I will save it as a PDF and I will put it into our class. There will be a folder in there that says class PDFs. And so, you know, not only will you have these notes, the typed up ones, everything I write down will also be put out there. All right. Let me get to a new page here. So let's talk about what you're going to do when you get home. Okay, what's your homework? Well, here's what I would do. What do we have scheduled? Look at your schedule real quick. What do we have scheduled for Wednesday? It says we're supposed to cover 1.4 and 1.5, right? So one thing that you'll need to do is watch the, what do I call them? Pre-class. Wait, is that what I called them? Shoot, I forgot. I think they're called pre-class videos for 1.4 and 1.5. And I'm going to put underneath there 1.3 because I didn't finish 1.3 today, right? So you should probably at least get through. I stopped at what, like 1.3.8 is where I stopped. So you should probably watch the video from like 1.3 6.9 on. Watch the pre-class videos. Where are those pre-class videos? I'm not going to tell you this every time. This is the first day, so I don't want anyone going home like, what the hell? Where do you find these? Where are they? There's a link in the syllabus, but there's also a link in Canvas, right? And it says in Canvas, what does it say? It doesn't say pre-class videos. It just says videos, okay? And then from there, it'll break it down. Let me see if I can't get in here. What the hell is that? This was the link in there that in Canvas takes you here, and this is where you had to go: academic affairs, math, mathematics, me, summer, Cal, and then there they are, pre-class videos. Right? Okay. So that's the link is in Canvas. What else should you do? Unit circle. That'll get you prepared. Now, homework. Actually, the homework problems that you should do, they'll come from 1.1 through 1.3. Normally, I would give them to you right now. Like I'd write them down end of class. I'd give you the homework. I don't have it ready yet. I wanted to kind of see how this first day went before I, locked myself in. So I will email these to you, and I will make an announcement. So it'll come in the form of an email, and on Canvas there's an announcements section. I'll put them in both places. Your homework for this section is. All right? Yes? I'll probably send those out, sometime today.
Okay, so that the homework will be like, it'll be due by then.
Well, I don't collect homework, okay? But that doesn't mean you're not supposed to do it. You should always do the homework for today and have it done by next class. So if you're in one of those situations where you're like, okay, every weekend is when I'm going to knock everything out, that might hurt you. You're supposed to cover it before you come back. So, yes, that answer your question? Okay, all right. I'm just trying to prepare you for, you're supposed to have done it. It'll come through your regular student.alamo. It'll come through that. Yep. So I'll email the homework assignment to you. Some other things. If you're interested, the CDF player, right? Do you want to download these things? Do you want to be able to click and drag things and arrows like I was doing today? You have to get the CDF player installed on your computer at home. Anything else here? The quiz, right? The quiz that's due. What's that quiz? Your life, right? Your life. I want to know everything about you now. There's something I wanted to add to this. I was thinking about this as I was walking in the hall. What's your major? I'd like for you to tell me what your major is. And then last math class. And what I mean by that is like what, when, and where. So your last math class was pre-cal during the spring 2013, right, here at Northwest Vista College, or pre-calculus in high school 13 years ago, right? I want to know like that sort of information. Yes. No. The last math class you passed. Yeah. Like if this is the 4th time you've taken this, you can share that with me, but I don't need to know that. Oh, no, on that quiz. with your life schedule laid out, just somewhere on there, just put like major, electrical engineering, you know, last class, pre-cal, summer. So that's the quiz. All right. Gosh, I feel like I'm forgetting something major here. I think that's it. You don't need to print out any notes, right? I mean, you have notes for at least the first chapter, so we're good till shoot, that's only like a week or two away, so you might want to print out the other notes. Now, I said in class, you know, no computers, right? You can't obviously use a computer or a laptop on a test, but if you download the CDF player onto a laptop and you want to follow me while I do notes in here and you want to have that, I'm okay with that. As long as it stays not you updating your Facebook, you know, hiding from me, that's okay. I think that's it. Oh, the video of today, right? That will be that same link that took you to the in-class videos. It'll be that same link. We'll bring up this page, and here it's class videos, right? Pre-class videos, class videos. So if you click on that, what I did today, what I said today, will all be there also. I think we're good. I'll hang out if you have any questions. Let me just stop my recording. If someone could hit the lights on the way out. Did everybody sign in? Anybody need to sign in?